Hey folks, welcome to Nuclear Chemistry. Since you're watching this, I'm assuming that you are on the last set of podcasts for chemistry. Congratulations. I'm excited for you. Fabulous job. All right, we're working here to get an A, so let's work together. We can finish this and you'll be on to bigger and better things. Okay, what are nuclear reactions? What's radioactivity? What's nuclear energy? What's the history of nuclear chemistry? Realize the history of nuclear chemistry is very recent. There hasn't been much done until the past 100 years or so. So this is kind of new stuff. Okay, so we're going to kind of give you an introduction here to what's going on with nuclear chemistry. So why do we want to study it? Well, the first thing is look around you. How does nuclear chemistry affect you? What are the positives and negatives of nuclear chemistry? Obviously, you've heard of some. You probably know about nuclear submarines. Nuclear submarines are submarines are powered by nuclear fuel. If you go and do any research on submarines, you'll find out that the diesel subs, which were the ones that were obviously common prior to nuclear, to be able to use their diesel engines, these were the ones that were used like in World War II. They had to go and be on the surface because they needed air to run the diesel engines because obviously they need oxygen. However, when a submarine went underwater, the moment it went underwater, it had to switch to 100% electrical power to go and run. Well, now with nuclear engines, the nuclear engines can be used underwater as well as above water, so that is much more reliable. Not to mention they don't use a whole heck of a lot of fuel. Right. We also have a lot of medical equipment, for example, MRIs that are done using nuclear energy and magnetism. Okay, so there's lots there that's helpful to us. Power plants. This is a picture of 3 Mile Island down in Pennsylvania. Again, another example of nuclear power where it's being generated. It's helping us. It's helping us here in Virginia because we have nuclear power plants here in Virginia that generate electricity, so we're dependent upon that too. Probably one of the coolest things I've seen is something called a cyberknife, which is at Carillion in downtown Roanoke, at Roanoke Memorial, or near Roanoke Memorial, at their cancer center. And it's used to eliminate tumors, for example, in the brain, where you don't want to operate, but they can go and, without doing any operations at all, they can go and kill tumors in the brain using something called a cyberknife, which uses gamma rays, and it's really amazingly cool. So if that's something you'd like more information on, come see me. I'll be happy to give it to you. It's really neat. And we do have a contact there, the head of the cyberknife division at Carillion. Both of his children went to Hidden Valley High School, so that's kind of cool. All right, now there are some negatives, of course, with nuclear energy. One, again, is power plants. They can explode. So here's an example of a power plant in the Ukraine called Chernobyl that exploded back in 1986. And the radiation from that has created a lot of birth defects in that part of the world. And here's an example of one that you see where the child is being cared for by this gentleman. Also, there was a nuclear radiation leak when there was a tsunami in Japan. That knocked out a reactor up in Japan, and they had radiation that we could detect all the way here in America because it traveled through the water to get here. So there were a lot of radioactive particles that got out and affected us as well. Another thing, obviously, is nuclear bombs. You can view that as a positive, or you can view that as a negative. That's certainly up to you how you view it, but that's nuclear as well. All right, so let's think back on chemical reactions. Chemical reactions, we know that we conserve matter. Matter is neither created nor destroyed in any chemical reaction. That was one of the rules that we learned. About chemical reactions. We also learned another rule, which was the conservation of energy, which said that energy is neither created nor destroyed in any chemical reaction. It simply changes form. So, for example, and the same thing's true up here, it's changing form. So, for example, if you think of probably one of the most common things that we think of that you've heard for years is C6H12O6, which is glucose plus oxygen gives you carbon dioxide and water. Let's just see. CO2 plus H2O. all right? And we conserve all the matter and we conserve all the energy. Now, you say, wait a minute, well, isn't this giving us energy? Well, yeah, it is. But what's happening is that energy is switching forms. It might be switching forms from chemical, because there's chemical energy stored in these bonds here, which is being released when we come over here. But that energy is switching forms to, for example, heat energy, which your body then uses, and it is still available, it's just in a different form. In nuclear reactions, matter is converted directly to energy. Matter is destroyed. It is not conserved. Now, only a small amount of matter is destroyed. All right? So some matter is destroyed, but only a small amount. But when it is destroyed and not conserved, it literally disappears. Well, where does it go? Well, it is converted directly into energy. So the matter is actually changing forms from matter into energy. And we'll talk about that a lot more in a future podcast. Right? Now, remember, in chemical reactions, you can't ever change an atom from one element to another, ever. That's the only reason that we can balance chemical equations. For example, if we have carbon as a reactant, it must be on the other side as a product. So when we look at this, we can see we have 6 carbons over here, and we have 6 carbons over here. And we have 12 hydrogens here, and right here we have 12 hydrogens. And we have 6 oxygens, plus we have 12 more over here for 18. Here we have 12 oxygens, and here we have 6 oxygens, again, for a total of 18. Matter is neither created nor destroyed, and we have the same number of elements of each kind on both sides. And that's the way we balance chemical equations. Right? Now, in nuclear reactions, we convert elements from one element to another. Really? So what needs to change for this to occur? How can we convert one element to another? How do we determine what an element is? Pause the video, think about that for a second. So how do we go and convert from one element to another? Well, if we started out with carbon, let's use carbon as an example, how do we know that something is carbon? Well, of course, it has 6 protons. So for me to convert it to another element, what would have to happen? Exactly. The number of protons would have to change. So instead of being 6 protons, it might be 7, or it might be 5. All right, so if we were to go to nitrogen, for example, it would have 7 protons. How in the world does this happen? Well, this is all nuclear reaction and nuclear chemistry. So what is a nuclear reaction? Obviously, it's a reaction that changes the composition of an atom's nucleus. We just went from 6 protons to 7. We changed what's going on in the nucleus, and hence the name nuclear. So when you're thinking about nuclear chemistry, we're talking about the nucleus. So something's changing inside the nucleus. This is absolutely radical, because everything we have talked about so far this year has been about electrons. Think about cations and anions and charges. We always talked about sodium having a plus charge and chlorine having a negative charge. And that's the reason they bond together. And then we looked at Lewis dot structures, and we said, well, we have oxygen. It has 6 valence electrons. So we always talked about valence electrons. And we talked about intermolecular forces. Intermolecular forces here are very strong. All right. Those are, that's actually an intramolecular force, is between these two ions, is positively and negatively charged. And then here we might have a covalent bond between 2 oxygens. And then our intermolecular forces, we're talking about covalent, we're talking about bonds pulling together one molecule, or one compound actually, a formula unit of sodium chloride to another one, versus what holds 2 oxygens to 2 more oxygens. Well, not a heck of a lot. And those are the London dispersion forces we talked about. We talked about what shapes we would get. For example, carbon doubly bonds to oxygen on both sides to create CO2, and it's linear. Well, what are we studying there? We're studying the number of clouds of electrons. And here we have 2 clouds of electrons, one on one side and one on the other, and that's why it's linear. Whereas if we have CH4, if you remember, okay, we have a total of 4 electron clouds, and hence we have something that is tetrahedral. All of that was about electrons. Our electron configurations, 1s2, 2s2, 2p6, that's all about electron configurations. Okay? So that's what we've been studying. Now all of a sudden we look at the nucleus and say, the nucleus is changing. The nucleus has never changed before. So what causes chemical reactions? Well, atoms bond together to become more stable. They gain, they lose, they share electrons. So if we think about what we have here with hydrogen, we have hydrogen bonded to hydrogen. We have another hydrogen bonded to hydrogen. And then we have oxygen. Let's say these are hydrogen. I'm too lazy to change colors. All right, remember it's doubly bonded to another oxygen. Well, these bonds break so that we can form two H2Os. So we have an oxygen bonded to two hydrogens. We have another oxygen bonded to two hydrogens. And again, we have 4 clouds of electrons, but only 2 of them are bonded, and hence we have something that is bent with 105-degree bond angles. All of that's chemical reactions. We're breaking bonds, we're forming bonds, okay? And the water is obviously more stable or has less energy stored in it, less potential energy than the hydrogen does and the oxygen does, because this gives off energy. It gives off a lot of heat, and that's what's coming out of the back of the space shuttle here is water. So what causes a nuclear reaction? Well, an unstable nucleus decays or changes in order to become more stable. This is called a radioactive isotope, or sometimes called a radioisotope. Ratios of protons to neutrons becomes unstable for some reason. In other words, it doesn't want to stick around. Really? Well, remember some isotopes? We talked about carbon and carbon being carbon-12, and we talked about why it wasn't 12 grams per mole is because like 99% of the carbon on Earth weighs exactly 12.00000 all the way out here, all right? But there's a little bit, like 1 or 1.5%, that weighs 13 grams per mole. And there's a really, really tiny amount that weighs 14 grams per mole. And believe it or not, there's even some weighing 15 or 16 grams per mole. All right? So if we look at carbon, this particular form of carbon, which is carbon-12, which has 6 protons and 6 neutrons. Protons are positive. Neutrons have no charge. These are the black ones, by the way, and these are the red ones. Right? You'll notice that it's 6 and 6. Okay? And that's perfectly stable. Now, we can actually add another neutron to this. This is to make carbon-13, and here's our extra neutron right there. Right? But this is still stable. So if we have some carbon-13 today, if you have some carbon-13 sitting in front of you, which, by the way, will look exactly like carbon-12, will act exactly like carbon-12, will bond exactly the same way carbon-12 does, it's perfectly stable, and it'll be here a day from now, a year from now, a million years from now. However, carbon-14 is different. What we do with carbon-14 is we've added 2 neutrons. Now, carbon-14 does exist in nature, but it's only a very little bit. And carbon-14 has a half-life, and we'll talk about half-lives in more detail later, but it has a half-life of 5,730 years, which means that over time, 5,730 years from now, if we had something that had carbon-12 in it, only half of that carbon-12 would be left after carbon-14 would be left after 5,730 years. All the carbon-12 and carbon-13 would still be there. Now, how about carbon-15? Well, sorry, this is carbon-15 down here. That's a mistake. This is carbon-15, and that's carbon-16. Right? We just added an extra neutron in both cases. Right? Carbon-16 has a much shorter half-life. Carbon-15 has a much shorter half-life. It's only 2.5 seconds. Right? So, any carbon-15 that exists in nature, it almost immediately disappears because in 2.5 seconds, half of it disappears. In 2.5 seconds, half of that stuff disappears. In 2.5 seconds, half of the remaining disappears, etc. So it gets small pretty quickly. But carbon-16 has an even smaller half-life. That only sticks around for 0.75 seconds. So if I had a brick of carbon-16, for example, in 3/4 of a second, half of it would disappear. And in another half a second, another 1/4 of it would disappear, and then 1/8 of it would disappear. So this would disappear pretty quickly. All right. So the bottom line is these nuclei that you see down here, they are unstable. All right. That is unstable. So as a result, it is going to tend to break apart because it has too many neutrons in it. Right? Think of it like glue holding stuff together. Well, what happens if you don't have enough glue? Well, if there weren't enough neutrons in here, it's going to break apart because there's not enough holding it together. What happens if there's too much glue? Well, if there's too much glue, the glue never sets. And the stuff that's in it that wants to be held together isn't going to be held together, so it's going to fall apart as well. All right? So we have to have just the right ratio of protons to neutrons to hold the thing together. So if we look at helium, for example, the most stable form that we find is helium-4. And helium has 2 protons, and since 2 plus 2 makes 4, that's where that 4 comes from, this has a ratio of 1 proton for every neutron. And if we look at carbon-12, which is again the most common isotope of carbon that we see, carbon is number 6, so it has 6 protons. It has to have 6 neutrons to give you the number 12. But look at potassium. Potassium is number 19, so that means it has 19 protons, but it has 20 neutrons. It actually has more neutrons. And in fact, because 19 plus 20 make 39. The further up on the periodic table we go, let's use xenon, for example, which is a noble gas, number 131. It has 54 protons. But its mass is a lot bigger than twice 54, which would be 108. So we actually have 77 neutrons. So notice what's happening is you have more neutrons than you have protons the bigger that you get. And in fact, if we go all the way up to lead, which is number 82 is going to have 125 neutrons. Well, notice that our ratio up here was 1 to 1. And our ratio down here is about 1 to 1.5. Right? And that's what happens as you get bigger. Right? And if you remember, uranium is the biggest thing, which is number 92. And our most common isotope is 230, I think it's 238, is our most common one. And when you get past 92 up to 93, those elements don't exist in nature. Why? Because they fall apart too easily. Right? There are just too many neutrons in there and too many protons, and they eventually just all repel each other and fall apart. All right, so the biggest thing that we have, the most number of protons that we have, is 92. If you look at your periodic table, you'll notice everything above that on the periodic table in our classroom is outlined. And on the periodic table that you tend to use, the masses that you're given are given to you in parentheses. You know, they might be given to you as 254, all right, in parentheses. And that's because that's an isotope that they make in a lab. Because they're all unstable. They all break apart. They're all radioactive. All right, so we have 4 types of radiation that impact us and that we're going to study. We're going to study alpha, beta, gamma, and positrons. We're going to talk about those in a future podcast. And they're all produced by nuclear reactions. Now, radiation, unlike chemical reactions, decay is not affected by temperature, pressure, catalysts, or the compound the radioactive element is in. All right, so when we think about we can speed up most chemical reactions by adding temperature, nope, doesn't help. We can go and change equilibrium by adding pressure or taking away pressure, nope. We can reduce the activation energy by adding catalysts, nope. Right, so all of these things, none of these things affect a a nuclear reaction. What compound the radioactive element is in? Nope, doesn't matter. It sure does in chemical reactions. So, unlike chemical reactions, decay is spontaneous. There is no activation energy. It just happens. Okay? And that's important to understand. It just happens. Decay just happens. All right, so think about spontaneous reactions. A match, when you want to burn a match, this does not happen unless you strike the match. Right? The match is not just automatically going to start to burn. However, this thing over here, this is uranium. Right? And uranium is just going to go and decay over time because it does. So let's talk about the history. This is going to be real short, just a kind of real short lesson on what happened in history. Henry Becquerel, back in 1896, he had some photographic plates, and they were stuffed inside an envelope similar to this manila envelope. All right, and he had the envelope closed so that it couldn't get any light to it. And when Becquerel wanted to hold the things down, he just threw a rock on top of it. Well, it was a piece of uranium. Okay, he didn't think twice about it, and it was near the photographic plates. And what he found out was that when he looked at these plates later, they were never exposed to light, but he found that they were frosty. They had an image on them that even though the picture had never been, he'd never taken a picture with it, right? And he figured out, and like you and I would just say, oh, stupid bad plate, wouldn't think twice about it. He, being a scientist, said, well, wait a minute, maybe it had something to do with this rock. So he performed some tests, okay? And when he performed some tests, he figured out that uranium was actually going and exposing the photographic plates even through the paper. So uranium is one of the naturally occurring radioactive elements. And the International Standard Unit for Radioactivity was named after Henry Becquerel, so it is named Becquerel. Now, this is the last piece we have for history. There was Marie and Pierre Curie, and they isolated both radium and polonium. Now, the Nobel Prize was awarded to the three of them, these two, the Curies plus Becquerel, for the discovery of radioactivity, and it was awarded in 1903. And Curie also won the Chemistry Nobel Prize in 2011 for radioactive element research. Now, she died in 1934. She died of something called leukemia, which is blood cancer. And we now know that radiation causes cancer. We can also use it to cure cancer, but it causes cancer. So now, Curie also has a radioactive unit used for measuring radioactivity. It's named after her, and frankly, that's the one we use the most, even though the international standard is the Becquerel. All right, that's it for history. That's it for this podcast. If you have questions, please see us in class, do the worksheet, and then go on to number 2. Have a great day. See you. Bye-bye.